Let us try applying Mason's rule to a more complex signal flow graph. Let us draw a graph with 2 input nodes and 4 other nodes. This is not necessarily representing some actual physical system, it is just an example to illustrate the application of Mason's rule. So, let us call the input nodes x1, x2, and let us distinguish the other nodes which are not going to be input nodes by calling them, say, y1, y2, y3 and y4. So, there are 2 input nodes x1, x2 and there are 4 other nodes y1, y2, y3, y4, and I am going to put transmittances between these nodes. As you will see, I will put quite a few of them crisscross going this way, that way. I could have made it even more complicated, but this is good enough. I am going to label the transmittances in just some arbitrary order as k1, k2, etc. So, how many edges do I have here? This is k1, k2, k3, k4, k5, k6, k7, k8, k9 and k10. So, I have 10 edges and 10 transmittances, and there are these 4 nodes y1, y2, y3, y4 which are not input nodes, and there are the 2 input nodes x1 and x2. Let me remind you what all this stands for. At the node y1, then we have a summation, and what is that summation? We have to look at all incoming arrows, find out what the transmittances are, and multiply by these transmittances the signals at the other end. So, we have y1 equal to k1 x1, because that arrow is coming in from x1 with a transmittance k1, plus I have this term coming from y3 k4 y3, and then I have a term, that is all. I have just these 2 terms coming in for y1. So, the equation for y1 is y1 equal to k1 x1 plus k4 y3. The equation for y2, it has more terms because there is k2 y1 and there is k8 y2. No, it also has only 2 terms. How about the equation for y3? Y3 has 1, 2, 3 incoming arrows. So, the equation for that node is y3 equal to k9 x2 plus k3 y1 plus k6 into y2. Similarly, y4 has 1, 2, 3 incoming edges. So, the equation for that is y4 equal to k10 y3 plus k5 y1 plus k7 y2. So, for each one of the 4 nodes y1, y2, y3, we have an equation, and there are the 2 input nodes x1 and x2 for which we have no equation. They are input nodes, there are no incoming arrows, so there is no equation. And now we would like to obtain expressions for the nodes other than the input nodes, which means in this case y1, y2, y3 and y4, the node signals, in terms of the input node signals x1 and x2. So, we will obtain expressions like y1 equals some quantity, which is what we will obtain using Mason's rule or Mason's gain formula, multiplying x1 plus another quantity or expression multiplying x2, and similarly for y2, y3, y4. Now, how is the rule to be applied? As I mentioned earlier, Mason's gain formula or Mason's rule is closely related with Cramer's rule, and Cramer's rule, if you remember, has a common denominator for all the unknowns. Each unknown is a ratio of 2 quantities, and the denominator quantity is the same for all these ratios, and in fact that is a determinant. Similarly, the numerator quantities also are determinants. So, in this case also we will first calculate an expression which is common for all these different multipliers. It is the common denominator of all of them, and as I told you earlier, it is very often called delta, because delta is the symbol that is often used for denoting a determinant. how do we determine this delta? For that, as I told you, we have to identify all the loops. We have to identify all the loops on the graph. Now, if you look at the graph, there are some loops which probably stand out very clearly. There are some others which may not stand out so clearly. So, one has to be very careful. There will be no loop involving x1 and x2. Why? Because they are input nodes. There are no incoming arrows, so there cannot be a loop involving x1 or x2. So, we can only have loops involving, say, y1, y2, y3 and y4, and these loops have to be obtained carefully, or as one says, they have to be enumerated or they have to be listed carefully, and if you follow a definite procedure, then one will not miss out any loop. So, for example, we can start with the node y1 and find out whether there are any loops which will involve y1. So, for example, from y1 I can travel to y3 along k3 and then come back to y1 along k4. So, that is one loop, and the loop gain for that loop is, say, we denote it by L1. So, that is going to be k3 into k4. So, here is one simple loop consisting of only two edges, starting or involving the node y1 and coming back to the node y1 through only one more node y3. We can ask similarly whether we can travel from y1 to y2 and then back immediately to y1. In this case, we cannot, because there is no direct edge between y2 and y1. What about y1 and y4 and back immediately? No, because y1 I can go to y4, but I cannot come back to y1 directly. So, there will not be any two edge loop other than the one that we have found out for y1. Now, we can go on to finding out three edge loops that involve y1, or alternately we can look at other two edge loops, if any. So, doing the same thing for y2, I can ask whether from y2 I can go to some other node and come back to get a two edge loop, and the answer is yes, from y2 to y4 and back. So, let us call that loop L2, and that gain of that loop turns out to be k7 into, or the transmittance of that loop or the loop gain turns out to be k7 into k8. From y2 to y3 I can go, but I cannot come back directly. From y2 to y1 I cannot go, otherwise I would have included it earlier. Similarly, from y3, are there any two edge loops? Yes, y3 to y1 and back, but that loop we have already seen, so we do not look at it again. From y3 to y2 there is no edge, therefore there is no loop involving only y3 and y2, and from y4 to y2 is the loop that we already found out. So, this exhausts all the loops which will have two edges, and now we can look for loops which will have three edges. And once again, one can do it systematically. For example, I can start with y1. So, I start with y1, then go to some other node, then go to yet another node and see whether I can come back to y1. And this, I am saying all the time, should be done systematically, although when the graph is still not too complex like the one that we have, it is complicated, more complicated than the one that we saw earlier, but it is still not too complicated. One can usually see all the loops and not miss out any one of them, but in general one has to take care and therefore do it systematically. For example, I can go from y1 to y2 through k2, then from y2 I have to come back to y1 through some edge. So, y2 to y3 k6 and y3 to y1 k4. So, that is a three edge loop that involves y1. So, that is our L3, and the gain of that loop is k2 into k6 into k4. So, that took care of a loop that enabled us to go from y1 to y2, then through some other node back to y1. Now, we can say, okay, y1 to y4, then to some other node and back to y1. Can I come that way? So, y1 to y4, of course I can go, there is an edge. From y4 I cannot go to y3. From y4 I can go to y2, all right, but then from y2 I cannot come back to y1. So, there is no three edge loop of that kind. So, y1 to y2 to y3 back to y1, y1 to y4 there is nothing, that is there is no three edge loop that involves y1 and y2. And what about y1 and y3? If I go from y1 to y3, then I already have found out one loop which involves this, but from y1 to y3 I can go to y4, but then I cannot go to y2. So that's it. This is the only 3-edge loop that involves the node y1. So now we can find out whether there is a 3-edge loop that does not involve y1, and therefore it must involve y2, y3 and y4. Now is there such a loop that involves the remaining 3 nodes y2, y3 and y4? The answer is yes. y2 to y3 along k6, y3 to y4 along k10, and then y4 to y2 along k8. So that's my 4th loop. I'll call it L4, and the loop gain therefore denoted by L4 is k6 into k10 into k8. Now I am going in the order y2 to y3 to y4. Maybe it's possible to go from y2 to y4 to y3 back to y2. I should check. Well, I can go from y2 to y4, all right, but from y4 I cannot go back to y3. So that loop y2, y3, y4 can only be traversed in one direction, namely y2 to y3 to y4, and not in the reverse direction. Not the same loop. It would have been if it were the case, it would have been a different loop, but there isn't any. So there is no way of going along a loop from y2 first to y4, then to y3, and then back to y2. So that exhausts all the possibilities. So we have 3-edge loops. Now can we have a 4-edge loop? Well, the 4-edge loop must involve all the 4 nodes, and so we can go through this exercise once again. Starting with y1, I had to go to another node, then a 3rd node, then a 4th node, and back to y1. Is it possible? Well, I can go from y1 to y2, then I can go from y2 to y4, but I can't go from y4 to y3 or even y1, so that's out. I can go from y1 to y4, from y4 I can only go to y2, and then from y2 I can go to y3, and then from y3 I can come back to y1. Now this is a node that one could have missed easily if one was not being systematic and careful. So we do have a 4-edge loop. What was that once again? It was y1 to y4, so the gain was k5, then y4 to y2, so the gain was k8, then y2 to y3, the gain was k6, and then y3 to y1, the gain is k4. It's not a straightforward rectangular kind of loop, but involves that butterfly kind of figure. In fact, one gets familiar with such things, and when you see a loop, then you see a particular configuration like a rectangle or a butterfly or shapes of that kind. Is there any other loop that is possible? So there is another butterfly that I see here, but that does not give me a loop. In any case, you should now go over this once again and make sure that these are all the loops that we have. I hope I have not missed out a loop, but I leave it to you to check it up and go through it systematically. Don't simply say yes, these are the loops and nothing else. Do it systematically the way I told you. Choose a node, say y1, then say okay, 2-edge loops, so y1 to y2 back, y1 to y3 back, y1 to y4 back. Are there loops? Then go to y2, 2-edge loops, y3, y4, then 3-edge loops, so y1 to y2 to y3 back, is there a loop? Y1 to y2 to y4, is there a loop? And so on. Do this systematically and just make sure that you have got all the loops. Maybe you would have found one more loop. Notice that all these arrows are one-way streets, so when one talks about a loop, the arrows have to be taken in the correct, in their actual direction. You cannot go the opposite way to an arrow. So we have found out 5 loops. So that will contribute to one term in that denominator delta. But there will be most probably many more terms. So what are they going to be? So the next thing to identify are pairs of non-touching loops, that is two loops which do not touch one another. Touch meaning they should not have edge in common, they should not have even a node in common. So we have to identify all such loop pairs and then take the product of the loop gains of these loops, find all such non-touching loop pairs, the product of the loop gains, and then add them up, and that gives us the next term in the expression for delta. So let us do it here, and since it will take quite a while to find out all of them, I will just take one or two and then leave it to you to find out the rest of the non-touching loop pairs. Here is the loop that we had identified as L1, and in fact now you will see that it would have been nice if I had written down what were the nodes that were involved in that loop. So that loop L1, which had K3 and K4, involved Y1 and Y3. So I can put it down in brackets like this, some notation to remind me that this was the loop involving Y1 and Y3, and in fact I could even write down how was that loop traversed. So either Y1 to Y3 or to Y1, or Y1 to Y3 back to Y1. No, the two are the same, there is nothing, but if there are three edges, then there could be two different ways of going around two different loops. Okay, so that is one loop. The second loop L2 involved K7, K8, that involved Y2 and Y4. Now by looking at the nodes, we can see that they have no node in common. We can also look at the transmittance expressions. They are K3, K4 and K7, K8. There is no transmittance in common either. So they do not have any edge in common, but we have to check that they do not have any node in common. So L1, L2, those two loops, one of them involves only the nodes Y1, Y3, the other involves Y2, Y4. So they have no node in common. Therefore, this is a loop pair which is acceptable for our next calculation. And so we will have to take the product of these two loop gains L1 into L2, that is K3, K4, K7, K8. So that will be one term in the expression that we are going to write. What about the next loop L3? I can do the same thing. L3 was K2, K6 and K4. So that involved Y1, Y2, Y3. Now obviously if I look at L1 and L3, my list tells me that they have two nodes in common. So L1 and L3 are touching loops. So I should not take that product L1, L3. What about L2, L3? Well, they also have a node in common, Y2 in common. So I should not take that product either. So far I have three loops L1, L2, L3, of which L1 and L2 are non-touching. L1 touches L3, L2 touches L3. So we got only one non-touching loop pair, namely L1, L2, the product L1, L2 from that. Similarly, one can look at L4. Now since L4 has three nodes, it will turn out in this case that it will have a node in common with each one of the other three loops that we already written down. And the last loop that we wrote down had all the four nodes, so obviously it cannot have any other loop which does not touch it. And so the second term in our expression for delta we are now ready to write. So let me write the expression for delta so far. Delta equal to, remember the 1, do not forget this 1, minus sum of all the loop gains. So in this case there are 5 of them. So L1 plus L2 plus L3 plus L4 plus L5. There is a minus sign which applies to the sum of all these loop gains. The loop gains themselves may be positive or negative. They may have a positive coefficient or a negative coefficient. That does not matter. We take them as they are with their sign, add them up. So 1 minus this sum. The next term is not minus now but plus. And what do we have now? We have a sum of product of loop gains of non-touching loop pairs. And we have identified, or we have found out, that there is only one such loop pair. So we have L1, L2. There is only one term. There is nothing else. L1, L3 touching, L1, L4 touching, L1, L5 touching, so on, L2, L3, etc. So there is only one term, no other term. Next, we will have to write down minus 3 non-touching loops. Now, can there be 3 non-touching loops? in this case? There cannot be, because the 3 non-touching loops will involve 2 non-touching loops. So they must involve L1 and L2, but the moment you have L1 and L2, both of them, all the nodes of the graph are involved, and so there cannot be 3 non-touching loops, and so there is no more term now, and there is no need to go any further. So this is the expression for delta then. This is the denominator of all those transmittance coefficients that we are going to find out. This is the determinant, sometimes it is called the determinant of the, or associated with the signal flow graph, delta. So that's a major part, that's a big job, and we have done it. Now we have to find out the expression for y1 in terms of x1 and x2. So first let's concentrate on x1. So x1 is my input node, and I want to find out that coefficient which multiplies x1 in the expression for y1. So what is it that I have to find out? I have to find out a forward path between x1 and y1. Forward path, or a path, and forward is not necessary if it's understood that you always have to follow the arrow, a path from x1 to y1. Is there any? Well, of course there is this path k1, but is that the only one from x1 to y1? In this case the answer is yes, that's the only one. So the forward path, there is only one, and it has transmittance k1, so there is the gain of the forward path k1. This will be multiplied by what remains from delta when we remove from that delta all the loops which touch this forward path. So this forward path from x1 to y1 has transmittance k1 and therefore has node y1 in it. What are the terms in delta which do not touch it? So they are loops which do not involve y1, and so what will remain from there then? Of course 1 remains, so don't forget this 1, minus from that summation L1 is out because L1 had y1 y3. L2 is okay because L2 does not touch or does not include the node y1. L3 is out. What about L4, K6, K10, K8? So here is K6, K10, K8, that's okay, that does not involve node 1. So L4 is okay. L5 is not okay because it has all the 4 nodes, so that is out. So 1 minus that plus loop pairs, but those which do not include this node y1, or in fact any node on that forward path, it should not touch the forward path. Now that's not possible because L1 itself has node y1 in it, so there is no term, so that's all there is. So we have the numerator k1 into bracket 1 minus into bracket L2 plus L4 divided by delta. This is the coefficient of x1 in the expression for y1. So y1 equals k1 into whatever that expression divided by delta into x1 plus the other term which is to be calculated now. So what is that other term? That's the coefficient of x2, the coefficient of x2 in the expression for y1. So what I have to do now is to find out forward paths going from what node? From the node input node x2 to the node which we are looking at, or for which we are writing the expression, namely to y1. So we have to identify forward paths from x2 to y1. And now here we may have to be careful because there could be more than one path. In fact, there is no direct path from x2 to y1. There is no edge going from x2 to y1, but that does not mean there is no path between or from x2 to y1. So here is a forward path, and we can, as we go on, we can label these paths. For example, the path that I had identified earlier, I could have called it P1. P1 was the only forward path from x1 to y1. Now I am looking at forward paths from x2 to y1. There may be more than one, so let us look at them. So there is a path that starts off at x2 then goes to y3, and then goes to y1. So this is one forward path. Let's call it P2. Now what is the gain of that forward path? That is, what is the product of all the transmittances along that forward path? So from x2 to y3 we have k9, and from y3 to y1 I have k4. So the gain for that is k9 k4. So that's the path from x2 to y3 to y1. Are there any other paths from x2 to y1? Well, of course, from x2 I can only go to y3. So if I want to get to y1, I have to get to y3 first. But then from y3, can I get to y1 in some other way? Well, from y3 I can go to y4, but it seems that there is no way of going to y1 unless I come back to y3. From y3 I cannot go to y2. So that's it. So there is only one forward path from x2 to y1, and that forward path has gain k9 k4. Now this forward path gain k9 k4 is to be multiplied by what remains from the delta when we remove all the loops which touch this forward path. So once again, that 1 is to be kept as it is minus what? Now here again I have noted down the nodes that occur in the forward path, namely y1 and y3. So I should only look at those loops which do not involve these two nodes y1 and y3, and there is only one such loop, and that is L2. So I will have L2. So I will have 1 minus L2. There is no other loop that I need to look at. Plus, are there any loop pairs such that neither of them involves any one of the nodes that occur along this path, namely y1 and y3? The answer is no. So that's all, divided by delta. This is the coefficient of x2 in the expression for y1. And so we can now put the two together and write down the expression for y1 as some expression or a coefficient whose denominator is this common delta multiplying x1 plus some other ratio whose denominator again is the same delta multiplying x2. And in this problem, for this case, namely when writing the expression for y1, there is only one forward path from x1, the input node x1 to y1, and only one forward path from x2 to y1. And therefore in the numerator we had only one forward path gain multiplied by what remains of delta when we remove some of the terms. Now there can be in some other cases more than one forward path. In that case, in the numerator we take each forward path gain, multiply it by whatever remains of delta, and add up these products. So for example, let us say we want to look at the expression for x1 y4 in terms of x1 and x2. So I want y4 equal to some expression into x1 plus some other expression into x2. y4 I want in terms of the two input signals x1 and x2. To find the coefficient of x1, then I have to identify forward paths from x1 to y4. There may be more than one. In fact, there is more than one. For example, x1 to y4, I can go from, of course, x1 to y1, I have no alternative, and then I can go over to y4. The gain of that forward path, now we have got so far maybe P1, P2, so we will call it P3. So the gain of that path is K1 into K5, and it involves the nodes x1, y1, y4. Now from x1 to y1 I have to go, but from y1 maybe I can go to y4 in a different way. In fact, from y1 I can go to y3. So x1 to y1 to y3 to y4. That's a path P4. And what is the gain of that path? x1 to y1 is again K1, y1 to y3 is K3, and y3 to y4 is K10. So there is one more path. Is there any other? x1 to y1 again. Now instead of y3 I can go to y2, and then from y2 I can go to y4. And what is the gain of that path? Let us call it P5, K1, K2 into K9. So that's the third forward path. So now when I write down that expression for y4 in terms of x1, in the numerator there will be 3 terms. Each one of these forward path transmittances will be multiplied by what remains of delta when we remove certain terms. So, the numerator now has more than one term, and so on. So, this is how Mason's rule or Mason's gain formula. As you can see, it is not quite a formula, in the sense it is not a ready-made formula, it is a rule. It is more therefore correct to call it a rule, and we can apply the rule to obtain these expressions for non-input signals in terms of the input signals. As you have realized, it requires great care to identify all the loops, then identify loop pairs which are non-touching, loop triples which are non-touching, and so on. Then to identify forward paths from an input node to a non-input node, identify all the forward paths, then check a forward path and a loop to find out whether they touch each other or not, because that is what is to be used when writing down the numerator expression. We only select those loop or loop gains or gains of those loops which do not touch the forward path at all for the numerator expression. So, all this has to be found out carefully, and then of course one can write down the final expression expressing a non-input node signal as a summation of input node signals multiplied by certain coefficients or effective transmittances from a particular input node to a particular non-input node. This is Mason's gain formula, or rather Mason's rule applied to a signal flow graph. You can compare this with what you would have had to do if you used Cramer's rule, or if you solved simultaneous equations in some way or the other. Going back, each one of the nodes has an equation associated with it, right? For node y1, I have the equation y1 equal to k1 x1 plus k4 y3, that is all. For node y3, I have a more complicated equation y3 equals k9 x2 plus k3 y1 plus k5 y2. Similarly for y2 and for y4. So, I will have 4 equations for y1, y2, y3, y4, in which the input signals x1 and x2 will also appear. Now, I can solve these 4 equations for the 4 non-input node signal unknowns y1, y2, y3, y4 using Cramer's rule or using some other technique of solving simultaneous linear equations. Will it involve less work or more work? Well, that really depends. It will involve work which would not really require looking at a graph, that is for sure, because when I have the equations, I do not have to look at the graph. So, it involves work of a different kind altogether. It does not involve looking at any picture or looking at any graph. And as I said earlier, and I repeat, the signal flow graph technique or the Mason rule is really useful when it is applied by human beings, by you and me, for small problems to get some understanding or some insight into what is going on. For a large number of signals and a large number of equations, drawing the signal flow graph and then looking at it is not a very good method, because as human beings, as you must have already noticed, with our 6 node graph, there are so many loops that one can easily get confused and one can miss out loops or make mistake and not realize that these 2 loops are touching, but include them their product in delta, or a loop touches the forward path but include that loop in the numerator expression, and so on. Such mistakes are very easy to commit when the graph has a large number of nodes and a large number of edges. So, it is not really something which is to be used no matter what the problem may be. And of course, if it is to be done by using a computer program, then there is no question of drawing a graph, because as yet we do not have programs which will take a figure as an input, especially a figure that may be drawn by hand like I have done, and then I can trace a figure on the computer screen all right, but I should have an intelligent program so that it will transform this information, which is in the form of the signal flow graph, into a set of equations, and then use some other appropriate program to solve the equations, which may be symbolic equations, finally to obtain expressions which are also symbolic, involving these coefficient letters like k1, k2 up to k10, and the 4 symbols for the non-input nodes y1, y2, y3, y4, and the 2 other for the input nodes x1, x2, and therefore finally display on the screen an expression like y1 equals, with that equality sign, some stuff multiplying x1 plus some other thing multiplying x2, etc. I am not aware of any program package that will do this job at the moment, although one can think of a computer program which is smart enough to accept an input, for an input, hand drawn or hand traced signal flow graph. The signal flow graph is traced on the screen with the help of a mouse, perhaps with any one of the graphic programs, and then the rest of the work is done by a program, so that you have a display of the final result. In any case, this may not be the best way of doing it, because equations can be solved in other ways, and especially if there are numbers rather than symbols, then all this is really not required. People have been solving simultaneous linear equations by computers for the last 50 years or more, and they have developed very good efficient methods for doing that. So there is no need to draw a signal flow graph and then apply any Mason's rule or whatever to it. Its main purpose will be to, for small systems or even for larger systems perhaps, to get some insight into what can happen and so on. And so after this little excursion into signal flow graph and Mason's rule and so called Mason's gain formula, we will get back to our feedback control system problem, and there we will apply, the system being small, we will apply Mason's gain formula or Mason's rule to get some result. We will also do it using block diagrams to show that one can do it with block diagrams, one does not necessarily have to have signal flow graphs. So let us get back to our example, and there we had decided that the two equations that we have, let me remind you what are the two equations. One was the armature circuit equation involving the applied voltage EA, the back EMF which was dependent on omega m, and the armature drop RAIA. That equation we solved for one of the two variables, either omega m or IA, in terms of the other two, and correspondingly started constructing a signal flow graph. So let us suppose that we have solved that first equation for omega m. So what will be the solution? Omega m will be 1 divided by kb into EA, and the other term is transferred on the other side, so minus RA divided by kb into IA. So that is the equation, first voltage equation for the armature circuit, solved for motor speed in terms of armature voltage, applied voltage, and armature current, and that resulted in a part of the signal flow graph that we are going to construct, namely with EA as one node, omega m as one more node, and IA as a third node, one arrow going from EA to omega m with gain or transmittance 1 by kb, and another arrow going from IA to omega m with transmittance minus RA by kb. So that takes care of that one equation. The other equation is the torque equation, and what is the torque equation? Once again, the torque produced by the motor Kt into Ia equal to the load torque plus the torque to overcome friction, and solving it for Ia, that was easy. We get Ia equal to 1 by Kt into TL plus Kf by Kt into omega m, and therefore on the signal flow graph now I can put two more edges to stand for this equation. This equation is for node Ia, IA equal to 1 by KT TL. So, I put one more node TL. Here is the edge from TL to IA, its transmittance is 1 by KT, that is okay. And then I have the other edge from omega m, Kf by KT. So, I have Kf by KT. So, that is my signal flow graph for the armature speed control problem, where we had only applied armature voltage and no feedback. The scheme was really very simple. Now, what was the goal of all of this? We wanted expressions for omega m basically, and perhaps Ia also, in terms of the applied voltage and the load torque, to find out how the speed will change if the applied voltage changes or if the load torque changes from the nominal or the rated value. Now, we will use Mason's rule for this purpose, and as you can see, the graph is very simple. So, the application will be very easy. First business is to find out that expression delta, which requires us to find out all the loops that there are in the signal flow graph. In this case, the graph being very simple, I can immediately spot one loop and only one loop. So, let us call that loop on the L. The loop gain L is simply the product of those two transmittances. So, it will be minus RA Kf divided by Kt into Kb. That is the loop gain L. There is only one loop. So, what is delta? Delta is simply delta equal to 1, do not forget this one, minus sum of all the loop gains. There is only one loop gain, therefore, L plus loop pairs, but there are not any loop pairs. Of course, when one says non-touching, they have to be distinct. So, L and L do not constitute a loop pair in that sense, and therefore, there is nothing else. So, delta is simply 1 minus L. We already have an expression for L. So, delta will be 1 plus RA Kf divided by Kt into Kb. So, that is the common expression delta. And now, we can write down the expression for omega m in terms of Ea and TL. To find the coefficient of Ea, we need to find out the forward path from Ea to omega m. Fortunately for us, there is only one forward path, and that is 1 by Kb. So, omega m equal to the expression multiplying Ea, the denominator of that will be delta, the numerator will be this forward path gain 1 by Kb. This forward path gain will be multiplied by what remains of delta when we remove non-touching loops. Now, the only loop we have has both omega m and Ia, therefore, it touches this forward path Ea to omega m. Therefore, what remains of delta is only 1. So, there is nothing there to write. Do not forget that 1. If you forgot that 1, you would have got 0 there, and probably you will get a 0 for your answer also. So, that is all there is for that expression. 1 by Kb forward path gain multiplied by only 1 that remains from delta divided by delta into Ea, plus the other term which multiplies TL, the load torque. For that, we need the forward path from the load torque node TL to the speed node omega m. Is there a forward path? Yes, and there is only one, from TL to Ia and then to omega m. And what is the gain of that forward path then? 1 by Kt multiplied by minus Ra by Kb. That is the gain of the forward path, only one. Then I have to multiply it by what remains of delta. Delta has 1 minus L. I have to only choose loops which do not touch this forward path, but this forward path involves both the nodes omega m and Ia, whereas the loop involves both the nodes omega m and Ia. So, what remains of delta? Once again, only 1. So, I will write 1 divided by delta, and that is the complete expression for omega m in terms of Ea and TL. Omega m equal to 1 by Kb divided by delta into Ea minus Ra by Kb Kt into delta into TL. With this expression, then one can look at what happens when Ea changes or TL changes or any one of the parameters happens to change. So, for example, if Ea changes by such and such amount and we can talk in terms of percentages, but we can also talk in terms of absolute value. In fact, this expression is such that it is easier to find out in terms of absolute values, but then one also thinks of percentage change as what is normally expected. It is not enough to say that something has changed by 50 volts, changed from what value? If it has changed from 50 volts by 50 volts, it has become 100 from 50, that is a drastic change. Whereas if it has changed by 50 volts from 1000 to 1050, that is not such a big change, although it is still a change of 50 volts. So that is why talking in terms of percent change or per unit change is also useful, but that is very easily related to the absolute change. So now suppose my EA were to change from 230 volts by 10%, so by an amount 23, so 230 volts plus 23 volts, my EA has become 230 plus 23, right. Now what will be my omega m? Now this expression tells you that omega m will change by a certain amount. If omega m was previously 1500 rpm, because that is the way the drive was designed, then now the new omega m will not be 1500, because this part EA has changed by how much? By 23 volts. And so by how much will the speed change? The speed will change by 23 multiplying this coefficient, whatever this coefficient turns out to be, putting the actual numerical values. If it is, let us say, 2, then the speed will change by 46 rpm. Then I can find out what percentage it is in terms of 1500 rpm and say whether that speed change is very large or it is acceptable. Say 46 rpm from 1500 rpm, the speed is increased, that is just about 3%, and it may be acceptable for a particular case. So with 10% change of armature voltage, I will have 3% change of speed. That may be acceptable. If it is acceptable, no problem, we do not have to do any redesigning, think of feedback or what not. Something similar for TL. If TL changes by such and such amount, by how much will omega m change? That can be figured out easily. The change in omega m will be simply this coefficient that multiplies TL into the change in TL. So in fact one can write things like delta omega m, the change in speed, if EA changes by a certain amount, TL remaining the same, will be that coefficient of EA into delta EA. Similarly, if TL changes, EA remaining the same, then delta omega m will be the coefficient of TL multiplying delta TL. And Mason's rule enabled us to obtain those coefficients rather easily in this case, although solving those two simultaneous equations also, I am sure you would agree, is very easy for you. You will not get bogged down with solving two simultaneous equations for two unknowns. But this was to illustrate the applicability of Mason's rule that we did it this way. But with a larger system, it may be advantageous to use Mason's rule, or it may be advantageous to write down equations and solve them. That depends on what the problem is, how large things are, etc. So we have now a way of figuring out whether the drive is satisfactory. For such and such change in EA only, what is the change in speed and is it acceptable? For such and such change in load torque, what is the change in speed, is it acceptable? One can think of what is called worst case scenario, that is EA changes and TL changes. For example, one can see, because of the minus sign that multiplies TL, that if EA increases and if TL decreases, then the speed will increase much more than it would have if only one of these two things had taken place. In the other direction, if the armature voltage goes down and at the same time the load torque increases, then delta omega m will be negative, the speed will decrease, and the decrease will be more than what would have taken place if you had only one of those two things happening. So the effect of disturbance inputs on the behavior, steady state behavior, and the performance can be found out, and one can decide whether it is good or not. If it is good, then there is no need to do anything more. The drive as it is okay. If it is not, then we have to think of something, and of course what we thought of was the feedback mechanism or the feedback control system. What about changes in parameters? If parameter values change rather than the signals or the variables like armature voltage and load torque changing, then what will happen to omega m? That also can be found out from this formula for omega m. The only thing is, the formula is not in a very nice form. It does not show omega m as some coefficient multiplying a particular parameter, like say the back EMF constant Kb, because the parameter does not occur in a linear fashion. As you will notice from the expression, delta has Kb in it, and the numerator in the multiplier for Ea also has Kb in it. So it is quite possible that Kb occurs in a not a linear fashion, and therefore omega m cannot be written as some expression which multiplies only Kb plus something else, so that we can look at change in Kb, say 10% change in Kb, or Kb changes by this much, what will be the change in the speed. So the expression is such, and we cannot help it, because the dependence of the speed on the parameters is not linear. It is not in our hands, it turns out to be non-linear. We can't do anything about it. Whereas the dependence of the speed on the armature voltage and on the load torque does turn out to be linear, and therefore the signal flow graph analysis could be done, because we simply had multiplying coefficients or transmittances, and therefore we finally got coefficients multiplying Ea and TL. So much for our drive without any feedback. Now suppose you find out that for the motor that we have chosen, for the armature voltage that we selected, and so on, the performance of the drive is not adequate. That is, for say 10% increase in load torque, the speed drops by an amount which is not acceptable. So now we have to use some other scheme. We have to adjust, make some adjustment in the system to compensate the change in the load torque from the rated or the design value, and we would like to do this adjustment or compensation automatically rather than manually. If it is to be done manually, if you remember, that is not a big problem. Of course we have to provide for it. The operator, if the load torque increases, simply increases the applied voltage, so that the two cancel off each other, and therefore the speed remains the same. But that requires two things. One is, of course, there must be an operator who is looking at the speed, who knows what is to be done and does it. Secondly, we have to provide him the means by which he will do it. That is, the armature voltage has to be made variable. If the armature voltage is the supply voltage coming from supply, and you have no arrangement of changing it, then the operator can only watch helplessly. The speed will change, he cannot change the armature voltage. So it is not enough to have an operator, you have to give him the means, you have to enable him to change the applied voltage. In other words, you have to build something more now, so that the operator will change the applied voltage. Now instead of an operator doing it, instead of it being done manually, we wanted it done automatically, and therefore we wanted not only feedback, whether an operator watches the speed or whether you have a tacho generator which gives you an indication of the speed, that is feedback. In one case it is manual, in the other case it is automatic. But we want the adjustment, or we want the compensation, or we want the change to be done also automatically and not by a human being. And therefore we have feedback which is going to result in a system which is an automatic feedback control system, not a manual feedback control system. And we had already thought of how to do it. We take the voltage from the tacho generator and connect it as one input to a device which we have called the comparator or the error detector, to which we give a constant reference voltage as the other input. This device produces therefore the difference of these two, ER, the reference signal, or R of T in general, minus the feedback signal, in this case the tacho generator voltage, and the difference is then amplified. That is how it appears on the block diagram. In practical terms, that difference voltage will somehow change the field current of the generator which supplies the armature of the motor. Remember Leonard, we are following his drive, that is, the motor is not given a direct fixed voltage supply, but is given a variable voltage supply coming from a generator. That generator in turn is driven by another motor, or it may be driven by some other prime mover such as an IC engine or a steam engine or whatever may be at hand. So that is the feedback scheme that we have decided to use, and therefore we have now a few more equations that we have to write, and so the next business will be to modify the signal flow graph to take care of these equations. So what are these equations? Well, what are the signals that we have introduced, the additional signals that we have introduced? We had introduced the error signal E, the error signal E. This error signal E was the difference of the reference signal ER minus the tacho generator voltage, and we could write it directly now as K tacho generator, that is some coefficient multiplying the motor speed. This negative sign is important here, as we will see, and that sometimes is referred to as negative feedback. That is, we are taking a difference rather than a sum. E equal to ER minus KT tacho generator omega m. So we have one equation now which we didn't have earlier, and we have two signals E and ER which we didn't have earlier. So we have to add to our signal flow graph two more nodes, one ER and the other node E, and represent this equation on that. So I will have ER, therefore there will be a transmittance from ER to E of 1, and then I will have omega m, there will be a transmittance from omega m of minus KTG. So this is an addition to the signal flow graph that I have to make. I have added two nodes and I have added two more edges. This is one equation, but there is one more equation, and what is that equation? That is the equation which represents that motor which drives the generator which feeds the armature, and the generator field current is then controlled by this or determined by this error signal E, and therefore we have simply written armature voltage EA equals KA times E. And that is a very simple equation, because that simply says that put between the node EA and the node E a transmittance KA. So I have to add to the signal flow graph now one more edge. No node is required to be added because E and EA are there on the signal flow graph already. I just add one more edge, and so my signal flow graph will now look like this. This was my earlier signal flow graph for the two equations without any feedback. Now what is it that I have had to introduce? I have this error signal E. From there to EA I have a gain KA. So there is that gain Ka or transmittance Ka from EA to E. That is one simple equation, and then E itself comes from the reference signal ER through a transmittance of only 1, and the feedback signal tacho generator voltage from omega m. So I will have that edge with a gain of minus K tacho generator. Okay, so my signal flow graph now has got modified by the addition of these two equations and by the addition of a few more nodes. The two nodes that I have added are ER and small e. As a result, now what has happened? Of course, the signal flow graph has become more complicated. It has more edges, it has more nodes. So when I work on it, I will have to be more careful. Secondly, you will notice that the node EA, which was an input node in the earlier signal flow graph, is no longer an input node, and that is correct, because the armature voltage EA is now not going to be kept fixed. It is going to depend on what is happening. It is determined through E. It will be Ka times E. E itself is determined by what is happening, because E is ER minus K tacho generator omega m, and that is the meaning of feedback. That is, Earlier EA was not dependent on the actual speed. Now we make it depend on the actual speed through this scheme. The scheme of course involves expense, it involves an additional motor generator set or a motor generator set or a prime mover and a generator and whatnot, tacho generator, difference device, maybe an amplifier, and so on and so forth. Now ER appears as an input to my signal flow graph, input node to my signal flow graph, and as we saw earlier it is called the reference input. It is not really an input to the system, but it is what you may call a set point input. That is, now if I want the drive to run at some speed other than the one for which I had designed it, then I will have to change ER. So ER is the set point input, and there is still one input node, and what is that input node? That is the input node TL, that is the load torque, because that can still cause disturbance. So we will have now two input nodes, ER and TL. ER is the reference input node and TL is the disturbance input node or the load torque input node. Now we can go back, apply Mason's rule and get an expression for what in terms of what. We are interested basically in the speed omega m. And what are the input nodes now? ER and TL. So I want an expression for omega m in terms of ER and TL. So something like omega m equals some expression, and by this time we know that it will be a ratio of two things. By Mason's rule, the denominator will be a delta for the signal flow graph, etc. So some ratio multiplying ER, the set point input, plus some other ratio multiplying TL, the load torque input. Once we calculate those coefficients, then we can find out the effect of load torque change on the speed and the set point change on the speed. So we can even figure out what should be the set point voltage for the speed to be changed to such and such value. So do this and we will get back to that confusion about steady state error, and we will see what is wrong and make changes accordingly.